Okay, I believe that we are now live. So yes, hello everyone and welcome back to this live work where today we're gonna be actually talking about um we are gonna be talking about polymers. So yeah, oh oh so yeah, last time I have also just discussed about about polymers, but yeah, at that time I don't really I don't really understand it, and so yes, I just actually just watch some more videos just to make sure that I can actually grasp, so I can just grasp all of the theories. And so yeah, we are. So yes, we are gonna be checking all of my answers. So yeah, let's see. Why do branch chain alkanes have lower melting points than straight chain alkanes of comparable molecular mass? The answer is the branch ones are harder to pack, which results in a lower melting point. And yes, this is true because yeah, basically for the branch one, they cannot actually pack much more. Yes, they cannot crystallize much more easily than than the straight chain. So that's basically the first answer. So yeah, we are pretty accurate. For number two, um, density and polymer properties. Polyethylene exists either as a linear polymer or as a branch polymer, which is the high density form. Explain. So yeah. Oh, so yes. For the one which has the linear one, it is it is packed much more um much more easily, which means that it has a lower density. So yeah, we can just change this guy here. Oh, something just happened. I still don't understand what just happened. So yes, this one here, linear packs more easily. And then for part B, invisible light, high density polyethylene is opaque while low density polyethylene is transparent. Explain. Because of the index of refraction. Index of refraction. LDPE has more crystallized crystallized spots, which makes it opaque. And then for the branch one, because because it doesn't pack easily, it is transparent because of its low density. So yeah, that's basically that. And then which form of polyethylene is mechanically more flexible? Um, well, with flexibility, I don't really know, but yes, for the form which has a higher melting point, I think I know what. So yeah, the higher melting point would be HDPE because of its van der Waals force is actually much more lower because of its low density stuff. So yeah, that's basically that. Um, for the branch one, polymers too. Let's see. Radicals, yeah. Which one is much more elastic? Um, Unfortunately, I cannot really tell. Uh, but I would say that I would say that the low density one should have a much more flexible stuff because of its branching, which means that which means that it can actually be shift from one to another. Well, yeah, that is that is my answer for number two. I hope that's correct. Number three, show how the following monomer can be polymerized. Which type of polymerization is used? So yes, for this one here, we use condensation because oh, because when you actually just see that the OH and the OH actually has it it has a pair, which means that they could which which means that they could actually just react just to form H2O, and then after that you have this oxygen bridge. And then for the polymerization, show how that is at that is ethene can be polymerized. What type of polymerization is used? We use addition because oh, oh, because I see the double bond, which means that using using a radical could work. So yeah, that's that. Okay. Next up, why do aldehydes and ketones have higher boiling points than alkanes or alkenes of comparable molecular mass? Um, because of its dipole moment. Um, yeah, but yes, according to my knowledge, these guys actually does that. Um, this guy has a higher boiling point because of its hydrogen bond, which which is very hard to be separated. How is increasing the mass of aldehydes of ketone is going to affect its melting point? Well, yes, according to logic, um, if you are going to be increasing the mass, the London stuff is going to be increasing as well, which means it's going to have a higher boiling point. So yeah, that's that. Compare boiling point of carboxylic acid to two similar mass alkanes and alkenes and explain the physical reasoning for the differences for the difference. So carboxylic acid, I actually forgot about carboxylic acid. Let me just go ahead and just try to find that carboxylic acid. Um, compare boiling point of carboxylic to mass and explain the physical. So yeah, the for me the boiling point would actually be similar to the aldehydes and ketones because of its hydrogen bonds. So yeah, that's basically that. But wait, what is aldehyde? Yeah, you could say similar to aldehyde and ketones because that's my logic. And then after that, we also got a question from the book Introduction to Materials Engineering. Let me just go ahead and just find the book first. Um, where is it? Um, where is it? Um, wait, what? Where is it? Literally, where is it? Oh, there it is. So let's go to 12.6 here. Okay, there it is. So calculate calculate the degree of polymerization for a low density polyethylene with a molecular mass with a molecular weight of 20,000 AMU, a high density polyethylene of 10,000 AMU, and then an ultra dense with 4 million AMU. So yeah, basically to calculate such things, let me just write that down. Calculate the degree of polymerization for a low density polyethylene 20,000 AMU, a high density polyethylene 300 polyethylene 300,000 AMU, and then an ultra high density polyethylene which has 4 million AMU. So to calculate the degree of polymerization, all all you need to do is to just to divide it by the mer, which in this case it would be ethylene. Yeah. So yes, you can just go ahead and just look at your periodic table and find that for carbon it would be 12.0107. Um, let me just plug into my calculator. 12.0107 times 2, because that we are actually trying to find the one for the ethylene. So yeah, and then you add it by 4 times the bond of hydrogen. No, sorry, the mass of hydrogen, which is 1.00784, which would mean that, yeah, the number would be, so yeah, for C2H4 it would be 28.0526276 AMU. And so that means that you can just actually just try to find the you can find the degree of polymerization. So so for part A, wait, first oh let me just mute first. Okay, let's see now. Um, 20,000 divided by the answer that you got there. The first answer would be for A, that would be 713. That is the degree of polymerization, but yeah, you're just taking the average, because like yeah, because like when you're actually just talking about polymers, you always take the average. So yeah, I just I just took like a number which in this case is 713. And so now let's go ahead and just try to find it for the high density polyethylene, which is 300,000. That's 10,694. And then for the last one there, that's 4 million. There we go. Which you got 142,588. Yeah, So yeah, that is the degree of polymerization, which is pretty accurate, I should say. But yeah, that is basically that. So yeah, that is for practice problem L that we try to practice. But now, let's actually go to the test. No, sorry, the quiz that. Sorry, the quiz that I'm gonna be actually trying to talk about how I actually think about it. So yeah, let's just jump straight into it. So so this is quiz 10. So let's just start. Circle the monomer in the following polymers. So yeah. Um okay. According to myself, okay. Um the mer here would be this guy here. This guy here. This thing seems to be the mer, but I don't think so because like yeah. Well, because like this thing is actually formed by yeah. Yeah. Yeah, that thing forms by condensation according to my according to what I see there. So it could be that, or it could be something like these guys here. I think those are the MERS instead. Because like yeah. Oh, because like yeah, this polyethylene glycol is actually made by condensation. Because like yeah, you can see of this hydrogen bonding there. No, sorry, the oxygen bonding. So yeah, that is from my intuition states that yeah, this thing should be like a this thing should be like a condensation type instead of the chain type because like yeah because because if it is a radical type, unfortunately the oxygen would be having too much electrons. So yeah, condensation is the best choice. For the second one here, for polystyrene, it would be this guy here. Huh. This guy here with the benzene ring. And so yeah, that's basically that. And so what is the primary intermolecular force in polystyrene? Um, you could say that this thing is London because like it only has like carbon and hydrogen. So yeah, basically London could be one thing and then it should also have dipole, but yeah, London would be the highest form. 1C. Which polymer would you expect to contain more crystalline regions? It is the one which is most ordered. So I- so so it would be polyethylene glycol, but yes, it is just flipped from bottom and then top and then bottom and then top. So yeah, it is not really that ordered. So yeah, I would say that yeah, polystyrene would be the answer. Polystyrene because of the orderness. It is isotactic. Which polymer would you expect to be soluble in water? Oh wait. Which polymer would you expect to contain more crystalline regions? Well, well, yes, I should say like 1C. Oh, like yeah, polystyrene would be having a lot more, a lot more ordered than polyethylene glycol, even though that it has that oxy, even though it has those hydrogen bonding. So yeah, I guess that I guess that would be the answer. Poly polyethylene glycol. Let's see. Well, yeah. Which one should have the more crystalline region? I should say polystyrene, which which is pretty accurate, I guess, versus polyethylene glycol. Like yes, like yes, I am just actually researching about this. I believe polyethylene glycol is actually a liquid, so yeah. So yeah, I guess polystyrene is the answer. Good. So yeah, I don't know if the answer is correct or not, but yeah. This is like how I actually think. Which polymer would you expect to be soluble in water? About so yeah, about solubility, it is about the lightness. So yeah, which one is actually much more light? And so yeah, the most light would be the polyethylene glycol. So yeah, that would be my answer. Polyethylene glycol. Why? Because of its hydrogen bond, similar to the water's hydrogen bond. One of these polymers is made via a radical process, and the other is made via a condensation process, which is made through a radical process. I know it to be polystyrene because that's basically addition. Because like yeah, you just start with a radical from that like styrene, I believe, is the monomer. So yeah, I guess that's that. Okay. Next up, in your goodie bag, you mixed Elmer's glue and borax, which is basically called slime. The relevant chemical components are shown below. We got Elmer's glue there, which is which has a backbone of carbon with some hydrogens and also hydroxides. And then also you got borax. So A, draw the borax component on the following strands of Elmer's glue. Okay. So okay. Uh so first thing that so yeah, first thing that I see is that this thing should be the hydrogen there. This one here should also connect to another hydrogen there. And then in here, like yeah, draw the borax component. Okay. So yeah, this is basically like the chain. That. And so you got that, and then you also got this um boron there connecting to a oxygen there. Like, like yeah. The problem is that this guy doesn't have enough space. So yeah, let me just shrink my. Nope, never mind. Let me just shrink this guy first. Oh, there we go. Nope. So yeah, with that I can just erase this part here. There we go. So I can add in my hydrogen, and then in here we got the hydrogen and the oxygen there connecting to the boron, and then in here you got another hydrogen, and here you got an oxygen there, which is connecting to the hydrogen there, which in here you also have an oxygen with also a hydrogen there, and then no, sorry, right over there, that's oxygen bonded to a hydrogen. So yeah, that's basically what I'm trying to do. Is that this guy is actually connected here, this guy is connected here, this one is connected there, and that one's connected there because of the hydrogen bonds. Like yeah, I know, my sketch is totally terrible. Good. So yeah, let's just actually do part B. Okay. The the below graph contains the elastic region of two stress strain curves, corresponding to regular Elmer's glue and Elmer's glue treated with borax. Clearly label the two graphs as treated or untreated. Okay, I actually forgot about how to do this, but yeah, luckily I have my notes here for me to reference on. Uh, let's see. Is that is that about glass? Oh, there it is. So the strain is actually the change of L over L, and then stress is the force divided by the area. Okay? So the force that's applied, which is M times A, which in this case the A is acceleration, that means that a higher thing would result into a cut. I think so. Um, that's the change of L with L. Um, if something's much more elastic, wait. Somehow my brain is actually crazy. I don't know how to read the stress strain curve. Ah, F is kx. So it can be revert back. Um, okay. Uh, oh wow. This requires me to think a lot. So when you, okay, so when you have a material and then you just give it a stretch of M, of the force M, no, sorry, of a force which is the acceleration of the object. This guy here means that if you apply thousands of force, it would break. But for this guy, if if you apply a thousand, oh, okay. So I believe this is a untreated one, and this one is the treated one. Because like when you actually just apply lots of force, it would end up splitting into two, or basically fracture point. But then when you actually just do the same, but if you use the same force to do that to a Elmer's glue, it won't actually tear apart. But yeah, it still actually does that. So yeah, I believe that's that. And I guess that's the answer of this two-page quiz. So yeah, that's a quick one. So yeah, I hope you guys actually understand this a little bit much more about polymers, as I have now understand a bit more. So yeah, I just want to say thank you very much for actually watching this stream, even though that I don't have any views right now. That's fine. But yeah, thank you very much, and I'll actually just see you guys later on. Goodbye.